Now that we have introduced general exponential functions, we're going to introduce general logarithm functions as their inverse functions. Specifically, we have seen in the previous video that if we fix a number a to be the base for an exponential, so this number a has to be positive and different from 1, then the corresponding function a to the x, the exponential of base a, is a one-to-one function whose domain is the entire real line and whose range is the positive reals. Because it's one-to-one, it has an inverse function that we're going to denote by log a, the log of base a, and of course it has domain the positive reals and range all the reals, and it is defined with the usual formula that we use to define inverse functions. In other words, the log of base a of x is y, if and only if x is a to the y. What that means is that the log of base a of x is the power to which we have to raise the base a in order to get x. So this function, log a, is called logarithm of base a, and a particular case we've studied before is the case of base e, where e is the Euler number, and then we get the natural logarithm. Of course, what matters here is this formula that defines inverse function, and because the log of base a and the exponential of base a are inverse of each other, it means that if I raise a to the power log a of x, as long as this expression is defined, that is when x is positive, it returns x. And similarly, if I plug a to the x inside the log of base a, it returns x. Now I said that the log of base a of x is the power to which we have to raise the base a in order to get x. So let's look at some examples here. What would be the log of base 5 of 25? Well, the question is, to what power do we have to raise 5 in order to get 25? To the power 2, because 5 squared is 25. In other words, the log of base 5 of 25 is 2. What would be the log of base 4 of 2? In other words, to what power do we have to raise 4 in order to get 2? This would be to the power 1/2, because 4 to the 1/2, that's root of 4, it is 2. What would be the log of base 2 of 1/2? In other words, to what power do I have to raise the number 2 in order to get 1/2? Well, 1/2 is 2 to the negative 1, in other words, this log of base 2 of 1/2 is negative 1. Okay, so let's look at the graphs of these logarithms of different bases. Here is a graph of 2 to the x, right? In other words, the exponential function of base 2. And we have seen in the previous module, when we were talking about inverse functions, we've seen how to obtain the graph of the inverse function of a one-to-one function. What we do is look at the line y equal x and take the reflection of our one-to-one graph with respect to y equal x, and that's going to give us the graph of the inverse function. In other words, the graph of the log of base 2 of x is going to be obtained this way by reflection about y equal x of the graph of 2 to the x. And so this is what it looks like. Because 2 to the x goes to 0 when x goes to negative infinity, that means that the log 2 of base x, the log x of base 2 goes to negative infinity when x is approaching 0 from the right. And then you see that this is a concave down increasing function with limit infinity. Now in the case where the base is less than 1, say for instance we look at the exponential of power 1/3, well, we can obtain the inverse function in the same way. Consider the line y equal x and take the reflection about this line of the blue graph. We obtain this red graph, which is the log of base 1/3. So the case where the base is between 0 and 1. And you see that in that case, as x is approaching 0 from the right, the values of the log are going towards positive infinity. And on the other hand, when x is going towards positive infinity, and the log is going towards negative infinity. Now, in general, we may look at how a change in the base affects the graph, the shapes of the graphs. And now I'm going to play a little animation where we have in blue the graph of the exponential of base A, and in red the graph of the logarithm of base A. And on the x-axis we're going to have a dot that represents the value of A, starting to a value very close to 0, and then A increases. So we're going to start with a value of the base that is close to 0, and therefore corresponding to the kind of case we are looking at right now. In other words, the exponential function is decreasing with a limit of 0 at positive infinity, and the logarithm has a limit of positive infinity near 0. And then we're going to increase the base and see what happens. Again, the red graph is the logarithm, the blue graph is the exponential with the same base.